When I figured that out, I shed a single tear. I was like, it's okay, grab it. And go. Stick to this.
Yep. The average value of a function. So let's start with average. What's average? Well, here's a bunch of numbers, x1 through xn. The average of these, the arithmetic mean, is defined by what expression? How do you find the average of a bunch of numbers? So I add them all up. And divide by how many there are, which in this case, there are n of them. I'm going to use my sigma notation. Write this kind of like it looks like a sum. So I've got the sum of the numbers xi, where I goes from 1 to n, divided by n. Okay. I'll take that 1 over n and I'll put it in front. So it looks like that. Here's my formula for the average of a bunch of numbers. Now, I want to ask a similar question about a function. But it says up here in the title of this section, the average value of a function, which means I'm interested in the numbers we get out. Graph this for me. Close enough. I want the average of the values that come out. But there are infinitely many of them. All right, fine. There are infinitely many choices. I won't make infinitely many choices. I'll make finitely many choices. I'll just pick a bunch of y values. And then I'll average those using this. In order to get a bunch of y values, I need a bunch of x values. I take the x values, I plug them in, I get the y values, I figure out what's going on. So, how can I choose my x values? I'm picking numbers between 0 and 3. I could just throw a dart at a dartboard, right? I know, I'll roll a die, a whole bunch. No, that'll only give me a whole integer numbers. That's not going to work. I need to pick number. All right. I need to select numbers from 0 to 3. And I kind of want to think of them as spread out across the whole interval, right? So let's space them the same distance apart. Say again? I'm going to pick them to be a little distance apart from one another. We call little distances something, delta x. Okay, wait a second. But I'm looking at delta x, and I'm saying to myself, I'm working on a given interval. How do I find delta x when I'm working with an interval? The distance from the endpoint to start point divided by how many I want. Oh, okay. In our case, that'll be 3 over n. Wait, hang on a second. Hang on a second here. If I'm doing an average, I had that formula for an average, right? That formula for an average. If I want the average outputs, I'm going to take 1 over n times the sum of all of my xi's, right? I have a 1 over n here. Can you rewrite this equation in the box to get 1 over n alone? I would divide by it, right? I'd divide by the b minus a part. If I took this and I put 1 over b minus a on this side, 1 over b minus, 1 over b minus a, delta x. let's put that back in our expression here. So instead of 1 over n, I now have 1 over b minus a times delta x. Delta x is a number, right? And it depends on n somehow. I'm multiplying all this crap together. Does it matter what order I multiply in? Let's put the delta x on the end. I saw that yesterday. The hell's that thing? Not quite. Not yet. It's a Riemann sum. If I want to get a better average, I should use more values, right? If I really want to get the best possible average, I should use all the values. Let's take n and 10 to 2, infinity. To get the b minus a off of the top here, I divided it to the other side. So now if I say, well, let's let n go off to infinity, then this doesn't become a Riemann sum anymore. It becomes an integral.
The difference between integral and the Riemann sums, that is an indefinite number.
Our actual definition of the definite integral said the definite integral is the limit of our Riemann sum as n goes off to infinity. So that's exactly what I'm doing here. I'm saying, oh, we're going to take that n, throw it off to infinity, and that turns our sum into an integral. I gave you an interval, right? I said we're going from 0 to 3. I gave you a function, x cubed. What's the average output of x cubed between 0 and 3? I can calculate that now. What is the antiderivative of x cubed? I was going to say it is x cubed already. X to the fourth over 4, evaluated between 0 and 3. So I get 1/3 of 3 to the fourth over 4 minus 0 over 4. And I get 6.75. Questions? This is an average. Problem stats question, what's an average? I've been giving them to you all year long. Every time we've done an exam, every time you've looked on Canvas, there's an average next to a grade, right? What's it mean? Say again? Technically, unfortunately, no. The middle number between the high and the low point is exactly the distance between them, right? So if I took an exam and somebody got 100 and somebody got a 3, I hope the average isn't 45 and a half. It's in a sense, it's a center, right? But it's not always exactly the middle. There are lots of different definitions of center in a statistics class. We talk about the mean, the median, the mode, the mid-range. There are all sorts of different definitions for the middle of a set of data. This is a weighted average. Think of spreading the numbers out on a number line. And at each number in your list, you put a little weight on the number line. So if I had all the grades for the people in this class, I'd say, oh, I have 33 grades. I lay them on a number line from 0 to 100%. I got a bunch of weights. Oh, you got a 78. We'll put you over here. You got an 82. You got a 47. You got a 12, whatever the grades are. Now think of that as a balance beam. I want to balance it. Where does my finger go to balance that with all those little weights spread out? My finger goes on the average. If you think of these as torque, pushing down weights, the distance you are away from the middle has to balance. And that's what an average gets me. An average is a balance point for the distribution of my numbers. That's the picture of this graph. The distribution of the numbers goes all the way up to 27. But there are a lot more low numbers than there are high numbers, aren't there? On this same axis, graph 6.75. Right, not directly under the light. Balance. If I think of this like I'm balancing the y values, take a look at some areas in this picture. We have an area up here. We could compute this average, couldn't we? We could compute this area. I could take the integral from wherever they cross to 3, and I could figure out exactly what this area is, yes? I could do the same thing here, couldn't I? But by the definition of this being an average, those two areas are exactly the same. If you had made this shape, x cubed, out of ice, and then let it melt, the water would be 6.75 high. Our average value makes for us a rectangle whose area is exactly the same as the area under this curve. Because the area under the curve is this thing, isn't it? And we want it to go from 0 to 3. Well, area is length times height. I just divided by the length. I must be getting the height. When we started area problems, I talked about the goal was to find a quadrature. It's a rectangle. Do it again. A number of different symbols are used for the average. I've used f of x with a bar over it because the symbol for average in all of my stats books is x with a bar over it. But some textbooks will, instead of writing f bar of x, some will write f average. Some don't even write out average correctly, in my opinion, just write AV. You'll see lots of different notations in the resources you find online. What is our average value in this case? Yeah, give me a number. 2.8 repeating. Anybody convert it to a fraction? What's the fraction for that? 26 over 9. How do I do this integral? Because you did it on your calculator. That's not going to help me if I can't actually show what the hell happened. How do I do this integral? I need to use substitution. Angela, what is my use substitution? So du is I don't have a 3, so I'll make it 1/3 du is x squared dx. I'll mess with it on the differential rather than in the integral. Okay, I get a 1/2 here. The x squared and the dx become a 1/3 du, which I can then take out front along with the 1/2 to make this 1/6. Oh, I typoed something. What did I do that I should not have? I did something wrong. If I leave them, though, I have to remind myself that I've left them. I left those as 0 and 2, right? I better say, hey, wait a minute, those are not u numbers, those are x numbers. Otherwise, I'll be dumb and plug in 2 and 0 in u, and I can't do that. Those are x's. I must indicate if I've changed the bounds, I need to make sure I note that. If I haven't changed them, I need to make sure I note that. Okay, now I can do this problem. X equals 0, x equals 2, u to the 1/2 du, antiderivative u to the 1/2. But I still have this 1/6 out here, right? So let's simplify that. 2 over 18 is going to give me 1/9. And if I want to do x, I should go back to x. And now I don't have to write x equals next to my numbers because my evaluation expression is in X. Two cubed. 8 plus 1 is 9. 9 to the 3 halves. All right, wait a minute. 9, a half power means a square root. Square root of 9. 3 to the third. So 3 times 3 times 3. 27. Put in 0. 0 cubed is 0. Add 1, you get 1. 1 raised to any power is 1. Create for me the same graphical image that we had for the x cubed example, for this example. And again, I see that same sort of behavior. I see this upper right piece that's above my graph. I see that balances the area below the line over on the left of the graph. Questions? Once more. The important thing to remember in doing this calculation is the minus signs when you put in the -1. -1 cubed is negative, but then I'm subtracting that whole piece, so all of those signs get flipped over to being positive. Draw me a picture. And again, I will claim this area up here, if I shaved it off, it would fill in that little ditch right there. Questions? Piece of cake. All three of the pictures we made have something in common. They have lots of things in common. The graphs were going up as we went to the right. So that extra bit was over there on the right, and the trough was on the left. But the horizontal line itself crossed the graph. Why? Because it's within the range. Because what's within the range of what?
The straight line is within the range of, like, the range.
The range of y's, right? The range of y's is my lowest y value, my highest y value. Doesn't it make sense for the average y value to be somewhere in the middle? If you had an average of 385 and your biggest number was 12, I'd worry what you did in your math. So yeah, because the average is between the low and the high. Well, wait a second. What did I say was another name for the average value? Arithmetic something or other? Mean. I've heard that word before in this class. Say it again. Mean value theorem. That means, that implies, there's a mean value theorem for integrals. Now, when we had Rolle's theorem and the mean value theorem, we had a lot more assumptions. We said that our function had to be continuous from A to B. It had to be differentiable everywhere between A and B. For Rolle's theorem, the ends had to be the same height. For integrals, we don't need any of that crap. I need the function to be continuous from A to B. That's all I need. Because take an integral, all continuous functions have an integral. I don't have to worry about the derivative part. What was our conclusion in the mean value theorem? What was our conclusion in Rolle's theorem? I know it wasn't on the exam, but we still need to know it. There was some value f of c between A and B. The slope of the tangent line was equal to the secant line, the one that went from A to B. The average value was equal to the tangent value at some point. The average value has to actually be taken on at some point. There has to be some x value, call it c, where that c has a y value that's exactly the same as my average value. So it works when I think about slopes. It also works when I think about outputs. There is always some point where that horizontal line crosses the curve. And I can find it. I can find it algebraically. I can find it using the technology on my graphing calculator. There's the problem we just did. Where did it cross? I can do it on the calculator. I can also do it in about 2 seconds by hand. What was this horizontal y value? 2. So I want 2 to be equal to 1 plus c squared. Because that's the graph, 1 plus x squared, right? That was easy. But wait, there's more. Plus or minus. Which means it crosses twice. Which I see in the picture, it crosses over here as well. And isn't that something we said in Rolle's theorem and the mean value theorem? There could be more than one, but there has to be at least one. And if I wanted to do that on here, because let's say we're doing the previous one with 26/9, right? If I was doing that expression, it would be 26 over 9 is equal to, c squared square root 1 plus c cubed. Nope. Nope. X squared square root 1 plus x to the third, 26 divided by 9. Where do they cross? Second, calculate intersection. That was easy. Is there an analytic way to do this by hand? Absolutely, but that means I got to square that right-hand side, square the left-hand side, and then solve a polynomial of degree 7. I think I'd rather hit myself over the head with a brick. This is the whole background reasoning. We started doing integrals to say, I can find a quadrature. I want to find an area. Literally. There's the rectangle that has the area I want. No matter what your shape is, if it comes from an integral, I can find the rectangle of the same area. I've solved the quadrature problem. As long as I knew the integrals. So, our next mission is to learn lots and lots and lots of other ways to do integrals, because there are still functions we can't do. The integral of e to the x squared. That's a really crappy looking 2 there. Or the integral of x times sine x. We didn't figure out how to deal with the product rule. U substitution only works for the chain rule, so I need to figure out how to undo the product rule. There are lots and lots and lots of other methods for doing integrals. But going through and solving all of these problems comes back to figuring out, is there an antiderivative? Is there a rule I can work backwards through? By the way, this problem, the answer happens to be no. There is no known antiderivative for this function, expressible in any of the functions we've used so far. If I really want to solve this using an antiderivative, I need to make up a new function. No, that's bullshit. I don't want to do that. Product rule, I'll figure a method out. And that's why we do things like Riemann sums, because there are some problems where I need to do this integral, and you can't, literally. There is no antiderivative that works. There are whole categories of these, things called elliptic integrals. Or Fresnel integrals. The emphasis here is on that word nice. Because if I really want to do a definite integral, I don't care what the antiderivative is. I'll plug it into a Riemann sum with n equals 10 million and let the computer chew on it for a week. I did that once. I don't recommend it. Took a PC overnight in 1980 something. If I threw it on Wolfram Alpha now, Wolfram Alpha might actually take 2 or 3 whole minutes. I did actually get a timeout from Wolfram Alpha the other week. I gave it a problem and said, nope, this is going to take too long. You have to pay for this one. Goodbye. One of my longtime friends got her degree in biochemistry, was studying, not biochemistry, regular chemistry, was studying long chain polymers, and looked at a spectrograph and needed the area inside the spectrograph to know the actual mass of molecules in there. So she needed to integrate something that came out of a spectrograph. I don't know if you've seen what comes out of that. Looks like a seismograph. All those spikes on it. You know what she did? She printed it out on filter paper. Because filter paper has a known density in grams per square centimeter. She cut out the curve and weighed it. And thus she knew its area. She then threw it on the computer, and it took overnight for her too, but it worked. That's published as part of her master's thesis. I cut this out and I weighed it, and the answer is this, so the area must be. I don't care what field you are going into, I have now solved the basic problems in all of calculus. You'll see them. They'll come up, unfortunately. Some of you will do lots more of this next semester, semester after, whenever Cal 2 shows up. I heartily recommend it. For those of you going on to do something like thermo or quantum, trust me, you want this. Cal 3 is absolutely going to make quantum and thermo trivial by comparison to this stuff. But that's only if you're interested in chemistry. Guess what, people? I'm done. Tomorrow is 6465. Bring me any questions you've got. The review sheet has been posted for well over a week. I will talk to you about that if you want to talk about that as well. I will also be glad to talk to you about that on Monday. You made it to the end of the semester, people. I'll see you tomorrow.